Hi everyone, and thanks for joining this session. My name is Manuel Martins, and I'm a senior analyst on the platform engineering team at ECMWF. Over the next 15 minutes, we'll focus on both the failures and successes of our journey from inception to production as we built the Kubernetes-native hosting platform at ECMWF. Who are we? The European Centre for Medium-Range Weather Forecasts is an independent, intergovernmental organization supported by 35 states. We are both a research institute and a 24/7 operational service, producing global numerical weather predictions and other data to our member and cooperating states and the broader community. We have offices in 3 countries, UK, Germany, and Italy, where we host our data center. We operate one of the largest supercomputers in Europe and one of the largest meteorological data archives in the world. What is this platform about? Let me start with a quick overview of our platform. ECMWF Sites is a self-service platform for creating and managing online spaces. It offers seamless integration with our production pipelines and allows users to publish and share all types of content. We have introduced it back in 2019 with 4 simple websites, and today it hosts more than 300. This graph shows the growth of the service from its early days. It reflects the gradual path to full adoption, which took several years despite the receiving great feedback from the beginning. We can also see a strong correlation with our reorganization into 3 offices in 2022. How everything started. I joined the web team at ECMWF back in 2017. At the time, we were essentially a DevOps team, creating and maintaining infrastructure to support research and development teams. We were responsible for several production web services, as well as parts of the infrastructure supporting these and other services. Most of the work back then involved creating and provisioning virtual and physical infrastructure for a variety of use cases, many related to web services. In our Jira backlog, we had many common requests for static file hosting or similar needs, and some of these requests had been sitting there for a long time. Naturally, when tickets stay in the queue too long, users tend to find workarounds. As a result, we had all sorts of content spread across multiple infrastructures and platforms, such as desktops running web servers hosting applications and static websites, software repositories used for hosting websites, Confluence pages filled with hundreds of gigabytes of attachments, etc. It was clear that we needed to come up with a solution. Back in 2019, when we first started thinking about creating such a service, we decided to build it as a Kubernetes-native application, a sort of experimental model for new developments at ECMWF. We had just transitioned our first Kubernetes cluster to production, so this was a great project to dive deeper into Kubernetes while building a solution for a real problem. We started with 3 simple requirements, covering more than 80% of the use cases we had. By early 2020, we released the first version of our new hosting platform and introduced it to a few teams internally. It gave us the chance to gather early feedback and collect more requirements for the platform. However, it was also at that point that we realized we made a fundamental design mistake. So what went wrong? At the time, the project was a single web application built in Python. We were managing multiple Kubernetes built-in resources, such as stateful sets, config maps, secrets, and persistent volume claims, each with its own configuration. We had not created a custom resource to properly represent the site, which we thought was not needed. With that set up, as you can imagine, the more features we added, the more complex and difficult it became to manage. And it quickly turned into a nightmare. We soon realized that we couldn't accommodate all the new requirements with the current design, so we had to redesign, rework, and migrate. And so we did. We redesigned and released version 2. We are now running a more fragmented architecture with components written in Python, Golang, and Lua. We kept most of the code base from the previous version and rewrote a few components. This time, we created a site custom resource definition, which contains all the configurations for each website. Of course, we still need to manage stateful sets, config maps, secrets, PVCs, and so on. But all of this is now handled at the operator level as part of the reconciling changes to a single custom resource. This means we now manage only one resource, the site custom resource, while the operator handles all the required configurations across the relevant built-in Kubernetes resources. As I mentioned before, the platform is fully integrated with Kubernetes and uses the operator pattern to automate and manage the creation of websites for users. All components have a REST API, allowing the use of our command line interface and software development kit for added flexibility. Looking deeper, the architecture of ECMWF sites consists of four main components: hub, operator, site, and jobs. The first component, the hub, is a centralized portal that aggregates all websites and allows users to view and manage their configurations, such as sharing, web analytics, and other technical aspects. It also provides administrative support for the entire system. It consists of three main applications: the web portal, an administration portal, and the REST API. The second component, the operator, is the core of the system and manages all the site custom resource operations, ensuring that each website is configured as desired at any time. Our operator includes several features to protect the API server, ensuring that only changes to the site custom resource that require reconfiguration of the website are managed. For example, we do not want to update any resource and reload the website configurations if the user only changes the description. The site component is the result of the operator component's CRD handling. Each website is composed of a set of containers running within a stateful set with some config maps, secrets, and a persistent volume attached. By default, a website runs four containers: OAuth 2 for authentication, Nginx with OpenResty for proxying and authorization, a web file browser, and a file REST API. Some websites may run more or fewer containers depending on their configuration. Finally, the jobs component is a set of tasks that perform regular operations, such as preloading web analytics, notifying users of certain events, such as when their storage quota reaches the limit, or when content retention dates have expired, etc. In terms of security, there are many features in place to ensure that websites are secure and accessible only by the intended audience. We use web standards for authentication and authorization. By default, users can only create private websites, meaning they need to be shared in order to be accessible by others. Converting a private website into a public one can only be done by a content manager to ensure compliance with ECMWF policies. We allow users to deploy their own applications as part of a website, and for this reason, we do not allow running containers in privileged mode, and this can only be configured on private websites. We have network policies in place to enforce internal traffic rules, blocking all traffic connections to and from each website, other namespaces, and components within the Kubernetes cluster. We have defined three levels of quality of service, each with its own priority class and resource allocation. This approach helps protect essential and high-load websites, as well as core components, while ensuring optimal resource management across the system. Now, how is the overall user experience? At ECMWF, we have different users with different backgrounds and use cases. So the service offers three main ways to interact with it. The simplest way is to use the web interface and the Hub portal to create and manage content. This is especially important for users without much technical knowledge. For more complex scenarios or cases that require some level of automation, users can either use the SDK or the CLI dedicated to interacting with the platform. Of course, users can also use curl and other command line tools such as LFTP, or even mount the website storage as a file system using DAVFS2 by enabling the WebDAV protocol on their websites. The command line interface is built in Golang and drops all the essential commands to interact with the platform. This is very useful for automated pipelines, allowing users to manage their websites from the command line. This example demonstrates the creation of a new website, followed by content upload and sharing it with another user. As for the Python SDK, it mimics the CLI as much as possible, allowing users to interact with the system using Python. This enables users to integrate the platform even further into other services or production pipelines. The same example is shown here in Python. As I mentioned earlier, of course, all of this is available through the Hub portal, allowing users to interact with the platform via their web browser. By accessing the Hub portal, users can list all websites and view their details, configurations, and all the URLs available. Here, we show how users can navigate through and access the various applications available for each website. With such a variety of users, the platform now hosts hundreds of websites with a wide range of use cases. Being a fully self-service platform, it enables users to take full advantage of its features, while allowing our content management team to keep track of our entire web portfolio. You can find more information about this platform by scanning the QR code. The linked article expands on this presentation, covering all platform details, user feedback, and performance tests. So, what did we learn from this project? We weren't expecting things to be perfect from the start. We were simply ready to change and adapt. It's okay to fail, but more importantly, to learn from it. Although we gained some early traction with our simplistic approach, we soon realized we needed to put considerable effort into improving the platform's user experience, while also repurposing it for use cases that we hadn't originally anticipated or advertised. Getting user feedback into production with short release cycles helped a lot with user satisfaction. And the fact that each website is completely isolated from the others also makes the platform highly resilient. Of course, there are still many improvements to be made, and we plan to continue investing in making the platform even better. Since then, we have built additional operators and controllers to support our managed infrastructure, all powered by the experience gained from this project. What's next? We plan to open source the platform, enabling other organizations to benefit from it. Of course, this involves significant work to abstract ECMWF specifics, but it's a work in progress. Expanding the platform's features and improving the overall user experience are important goals, and no matter how much we improve, there's always room for more. To wrap up, this platform has transformed the way users collaborate at ECMWF. Today, it supports far more use cases than we initially planned and has become an integral part of daily life for the ECMWF community. We are proud of how far the platform has come and even more excited about where it's heading. That's it for now. I hope you enjoyed hearing about our journey. Thank you.